In August 2022, many of us did not pass the analysis qualifier, as I've previously mentioned. And the instructor that taught us analysis that year leading up to the qualifier wanted to help us. He could tell that we were weak in a lot of areas, and he wanted to basically run a test course that he believed that many incoming graduate students would benefit from. And so it's kind of being workshopped right now, and essentially I am one of his guinea pigs, me and a couple other grad students. And so what he's doing is he's running this course informally. It's more like a recitation session, if you want, where he talks about various analysis related concepts, and then he gives us some exercises to do. So all of this is off the books. We don't get graded on it. We do problems casually, although I think he might be getting agitated at us because not enough problems are being solved. But last week, and I think by last week I mean this week, no, definitely last week, I decided to do one of his problems because I was familiar with it. And so I thought I would show you some of the exercises he gives us so you can get an idea of what he wants to do with this class. So he gave us a bunch, and I'm going to go through them here so you can read it. Okay, what's the first problem? Left continuity at x. So he defines left continuity, familiar analysis term. And we start with problem number 100. Why do we start with problem number 100? It's because that no one could remember what number we were on, so he started at 100. That's the only reason. What does the question say? Let EL and ER be subsets of the unit interval. They're countable and disjoint. So they don't overlap one another, and they're countable sets. We want to construct a function on the unit interval such that f is only left continuous on EL, and f is only right continuous on ER, but f is continuous on the unit interval. Get rid of the union of those two sets, so the complement. I think maybe this problem was proven, or solved, I should say, by one other guy in the recitation session. I forgot what the order of these problems were because, again, this paper is wrinkled. Because for one, it's been floating around in my backpack, and I haven't looked at the problems in a minute. So I was confused as to which one he did. I wasn't paying too close attention, I'm going to be honest. Sometimes that happens. Problem 101. F is a function. DL is the set of all points in the unit interval where f is not left continuous. DR is the set of all points that are not right continuous. It is known that DL is at most countable. Does it follow that DR is at most countable? I don't think anyone's done this problem yet. Problems like this just give me a headache that I look at. Normally I'm pretty comfortable with cardinality and problems involving cardinality. But this problem here, I just look at it and I stare blankly at it for like 5 minutes before I actually write something down. I also don't really like questions that follow, basically the question is, does something exist? Prove whether or not some qualities holds, or say something about it, because it doesn't really point you in any direction that you obviously need to go. Like for example, if this DR was at most countable, let's say, and the problem says, prove that DR is at most countable, then I feel like I have some sort of direction to go in. And I understand why some of these questions are worded like this, because in research, when you're doing research, you don't know what direction you're going in. So because you don't know what direction you're going in, you have to be able to keep yourself afloat when you're doing research, if that metaphor made sense. Like if you find yourself stranded in the ocean, are you able to get your bearings and swim back to shore? Because most of the time you don't know where the shore is. You have to figure it out. Okay, enough metaphors. Let's look at more problems. 102, f is the Dirichlet function. Problem A. For any x in the real numbers, prove that the limit is equal to something. Find the limit, I guess. I think that same guy that did 100 did part A of this guy. I remember him playing with him. I don't know if he completely finished it, but he got like all the way close to the end. I'm not sure. Is it possible to find a sequence of continuous functions fn such that for any x, fx is equal to the limit of fn? I believe I've seen something like this on Wikipedia, which means I might be tempted to do part B if he didn't do part B already. Again, I really wasn't paying that close of attention during the recitation, which is not good, I admit. But I plead the tired card, I guess. I get tired and then I don't pay as close attention as I should. But if this one's still open, I'll probably give it a go. Problem 103. Define a function from the unit interval to the real numbers such that any open subinterval that's not empty contains both continuum points of continuity and continuum points of discontinuity. This one seems kind of interesting, actually. And it's got to be true for any open subinterval. All right, this one's kind of intriguing. I might give this one a stab. All right, 103. I'm going to try and do you this weekend. But there's other problems, so we'll look at them. Maybe something else will strike my fancy. Problem 104. F is a continuous function on the non-negative reals. For any x in non-negative reals, the limit of fnx exists. Prove that the limit exists. This one also seems kind of familiar, like I saw it floating around on the internet somewhere when I was preparing for quals, but I don't remember how to prove it. It's also, I don't find it as interesting as 103. 105. F is non-negative to reals. It's continuous. F of x plus h minus f of x tends to 0 as x tends toward infinity for any h. Prove that f is uniformly continuous. I think someone started this one and didn't get it solved. Or maybe somebody told me that they were working on it, but hadn't finished it yet. Again, this recitation session, my classes kind of take priority, obviously, because that is on the books. So I think about stuff like probability theory and analytic number theory a lot more than the recitation session. But every few weeks, I'm like, okay, I got to get up to the board in that class and prove something. 106. F maps from reals to reals. For any x in the reals, f of x minus h plus f of x plus h minus 2fx tends to 0 as h tends to 0. Prove that f of x is a linear function. Yeah, this is another one. Okay, f is also continuous. This is another one of those problems where I'm kind of like, I'm not interested. And I wish I could quantify, or qualify, I should say, what makes a problem interesting to me. But it's kind of like gut reaction when I look at a problem. For me, I like I've said this before, I like math problems that are puzzly. And this one just seems like more of a headache than anything. I guess I could go through each of these problems, like what my gut reaction is. And then this one was just scratch work until we made it to 107 and 108. So 107 is show that this function here is infinitely differentiable. It's essentially the bump function. And 107 was the one that I did up at the board. So I'm actually going to show you the proof of it here in a minute. And I'm going to try and go through it quickly because it takes a while to do. I actually was going to write it up during this video, but it was going to take too long. So I'm just going to go through it step by step. It's actually the red stuff underneath. And then 108, what happens at the jump? Now this one is not very well defined because there's a lot that was on the board that I did not write down. So I can't answer 108. I didn't take good notes. Therefore, I'm not going to attempt this problem. It was about the convolution because I had asked him to review some stuff about convolution because I'm not very strong with it. And I actually didn't know that my problem was about convolution. I was really just interested in figuring out how to define a function that has jagged corners in it, and I wanted to be able to smooth out the corners in some way. And you do that using a convolution, which I didn't know. So when I asked him to cover that material, he obliged me and showed me how to do it. And then he asked this problem related to it, and I didn't write down good notes, unfortunately. Let this be a lesson to future grad students. Take good notes. Don't be like me. And then you end up having to read all these books to fill in the details. Okay. So if I have to give you just like my gut reaction as to whether or not I find a problem interesting, this is what I'll say. I find this one moderately interesting. I like the idea of the countable sets and the jump problems. There's a very and the way the guy that did it up at the board was a nice way of doing it too. I like the way he did it. This one, again, the question, does it follow DRs at most countable, is kind of annoying, so it turns me away. 102 I like because it's the Dirichlet function, and I find functions that are weird like that kind of interesting, so it makes me want to learn more about it. 103 I like. I'm going to try and do that this weekend. 104 is okay. I'm kind of meh on it. 105 is meh. 106 is meh. The bump function one I like because, again, it's about functions that have really nice properties in constructing them. And then 108, I don't really remember what the question was, unfortunately, because I didn't take good notes. Anyway. So now comes the fun part. We're going to construct the bump function. So what is a bump function? Now, I didn't answer exactly the question that he posed in class, but it's close enough to the part where he gave me credit for it. So what's the bump function? We want to construct a function that is real valued of a real variable, and it follows the 4 criteria. Criteria number 1. Apparently, I did not write the number 1 here. There. We want to make a function that's non-negative and bounded above by 1 for all inputs. We want the input at 0 to be 1. We want f of x to be equal to 0 for x outside of the unit ball centered at 0. And we want it to be infinitely differentiable. In other words, we want it to be really, really smooth so we can take as many derivatives of it as we want. And I drew a picture of what this guy looks like. He basically looks like a mound where he reaches 0 at 1 and -1, and then he just stays 0. So this is our bump function, and we want to show that this thing exists. We can actually make it. Now, we'll do it in parts. For full disclosure, I got this proof from this book, which I used in my real analysis, or my undergraduate real analysis class. So in this book, I'm quite comfortable with because I knew the author, so I'm used to it. Well, used to it's not a good way of saying it, but I like the book. It's got a lot of nice exercises in it, like this one here. Okay, step 1. There's 4 steps, by the way. We consider x positive, and we're going to apply Taylor's theorem and the Lagrange remainder to make the following inequality. We start with x to the n over e to the x. Why we are considering this will become apparent later on down the road. Again, analysts like to pretend they know what they're doing for a long time until they get to the end, but just remember they looked at where they wanted to go and then backtracked to figure out how to get there. So we have x to the n over e to the x. And we can rewrite this as x to the n over the Taylor series expansion, plus whatever this remainder is. So it's a finite Taylor series expansion, plus this remainder bit. That's the Lagrange remainder part. And then we say that that's bounded above by x to the n over that fraction. So I only took a piece of what was down here, and that's fine because if you make the denominator smaller, the overall fraction gets larger. So I just removed a bunch of stuff in the denominator so that the inequality held. And then if you just do a simple algebra reduction, you'll see that n plus 1 factorial divided by x bounds above this guy. So this part's just algebra. So the next question you're asking yourself is, why on earth did we do this? There's no real reason at the moment why we've done this. Well, it becomes apparent here in a second. So as x gets really large, this fraction tends to 0 because e to the x overpowers any power of x, any power function. And it's not too hard to see that if we have a polynomial, which we call px, then px divided by e to the x also tends to 0, because you can just split up that fraction into like the constant times x to the n over e to the x, and then those fractions tend to 0. So this guy tends to 0. Okay, now we make a very elementary observation. If x is bigger than 1, we know that x squared is bigger than x. And because of the increasing property of the exponential function, we know that e to the x squared is bigger than e to the x. Okay. So, we know that 0 is less than or equal to the absolute value of our polynomial divided by e to the x squared. That's just true because this is non-negative and that's non-negative. This guy is, okay, that part doesn't matter. But we can replace the denominator with something smaller, like e to the x. That's that part up here. And that this guy tends to 0, because we just showed that. We just showed that from right over here. Okay, so we know that this fraction is getting sandwiched between 0 and 0 when x gets large. Now we're kind of doing a t substitution or u substitution, but we use t here instead. When t is positive and descends towards 0, we see that 1 over t tends to infinity. Therefore, for any polynomial p that we choose, we have that p of 1 over t times e to the negative 1 over t squared tends to 0 as t descends towards 0. So in a sense, we're replacing x here with 1 over t. That's all we're doing. There's nothing tricky going on here. We're just replacing the x with a 1 over t. And it's not too hard to show that if t is negative and ascends up to 0, we get the same result. Partly because we were considering our absolute values up here. We're sandwiching this magnitude between 0 and 0. All right, are we ready for step 2? Yes, we are. So what's step 2? Step 2 is sort of like a stepping stone to figure out what our function's going to look like. We consider the following function f of x. F of x is going to be e to the negative 1 over x squared when x is not 0. Okay. Now we take its derivative. Its derivative is equal to this. All you need is calculus. Just use the product, or not the product rule, the chain rule. So apply the chain rule. We get this dude. And if you take the second derivative, then you have to apply chain rule and product rule. And we get something that looks like this. So I'm just using product rule here. And then you can rearrange some of the terms together. And we get something like this. Okay, so now we need to point something out. Notice that in the first derivative, we have, let me cover up a piece of this here. Here, to the left of my finger, we have a polynomial of 1 over x. And down here in the second derivative, we also have a polynomial of 1 over x. It doesn't look like a polynomial because we're used to seeing the variable as just like an x or a y or a u or whatever. But remember, it's a polynomial of 1 over x. Kind of like this guy up here. This is a polynomial of 1 over t. This is a polynomial of 1 over x. And this is why we go through all of this up here, because it comes in useful down here. Let's see here. Move this off to the side. Cover this up. Where is step 3? Oh, step 3 is here. We can use induction to show that for any derivative that we want to take of fn, we get some polynomial of 1 over x times the original function f of x. I skipped this induction step's finer details, but I think it's quite obvious to see, and this proof already takes 3 pages, and we're at the 20-minute mark. So I want to be as brief as possible without going over too many finer details. Okay, so we know we can take a lot of derivatives, and that polynomial Qn gets more and more terms every time. What is step 3? Step 3 is where the things start to get interesting. In step 3, we define psi to be this e to the negative 1 over x squared when x is positive, and 0 everywhere else. And then we make some interesting come on brain, do something amazing for once in your life. Observations. Couldn't think of the word. We notice that our function psi is infinitely differentiable outside of 0. And we also notice that psi is continuous at 0. How do we know that? We know it from step 1. Because we showed that in step 1, when t tends to 0, the product of these qn's and the fx's, they tend to 0 as well. Hold on. Let me make sure I didn't say anything I didn't mean. No, that's good. That's from step 1. They tend to 0. So psi is continuous at 0. We see that the polynomial of 1 over x is equal to 1. And we make the following claim. Psi is differentiable at 0. We need to show it smooth there, or else this falls apart. To show that it's differentiable, we set up our quotient. Psi x minus psi 0, divide by x minus 0. We can clean that up a little bit and show that it's equal to 1 over x times psi x. And by what we did in step 1, we know that that tends to 0 as x tends to 0. So we know that the first derivative tends to 0. Now what about the second step? We're going to take the second derivative, which means just take the derivative of the first derivative. So we set up this fraction here. We already showed that that's 0. This is just 0 here. And we know what psi prime of x is, right? Because we just showed that it's up here. So we end up getting this guy. So its derivative, oh, excuse me, I said that wrong, didn't I? We showed that, what's psi prime? So psi of 0 is 0, so we end up with psi x over x. So that kind of serves as our derivative. Or our derivative is this guy, right? Q1, 1 over x psi x. And then we have this x down here. Okay, all right, I'm with myself now. I forget how to prove things. I just automatically proved. Okay, so this part here, that's like our p of 1 over x. This is a polynomial of 1 over x, and when I divide by x, that's still a polynomial of 1 over x. Just like when you multiply u by a polynomial of u, you get a polynomial of u. Okay, again, by step 1, we have a polynomial of 1 over x, we have psi x, that tends to 0 as x tends to 0 as well. So now it's starting to become clear as to what's going on here. We can use induction again to show that the nth derivative of psi evaluated at 0 is again equal to 0. I leave out those details because again this is going on a bit long. Okay, next thing. We have the following claim. Psi maps the negatives and 0 to 0. But that's kind of obvious, right? Because that's how we defined it up here. Psi is already 0 when x is negative. So there's really nothing to prove for this guy. It's really just this guy that's interesting. But the proof is pretty straightforward. You just make a couple observations. The function negative 1 over x squared is strictly increasing from the positives to the negatives. And because exponential function is a strictly increasing function from the negatives to the unit interval, we know that this guy, apparently I started to write it as exp because I didn't want to write e to the negative 1 over x squared. But whatever, it means the same thing. We see that that function is strictly increasing from the negatives, or excuse me, the positives to the unit interval. And I make the claim that the other case is from the definition. So that claim really wasn't much, but it is important to note. All right, we're in the home stretch. Don't click off the video now. You've made it this far. We're about to make the bump function. All right, so step 4. Step 4 is where we actually define the dang thing. So we define phi to be real to real, and it's defined as such. Phi of x is equal to e squared psi of 1 plus x times psi of 1 minus x. And then we make a series of observations. Okay. Phi is continuously, God dang it. Phi is infinitely differentiable. That should be obvious because e squared is a constant, psi is infinitely differentiable, psi is infinitely differentiable. So because of that, we know phi is infinitely differentiable. So it's smooth. So that's the first thing that we wanted to show. If x is bigger than 1, then 1 minus x is negative, which means that phi x is equal to 0. This is because psi of 1 minus x is equal to 0. So this guy kills it. And then when x is big, meaning, or excuse me, the other direction, when x is small, less than or equal to negative 1, this piece kills it. So when you're far away from 0, which means magnitude bigger than 1, or equal to 1 for that matter, this function dies. It gets killed and goes to 0. All right, now what about phi of 0? If you plug in 0 into the function, you'll get e squared psi 1, but psi 1 is just e to the negative 1. You just plug it into the function, that's all you get. So you get e squared times those inverse e's, and that gives you a 1. That was the motivation for the e squared over here. Your bump function doesn't have to have magnitude, or excuse me, not magnitude, but maximum 1. It's just that the one that we wanted to build in the book had, peak at 1. You can choose any peak that you want. All right. Fourth claim. For any x, phi x is positive or non-negative since 0 less than or equal to psi x for all x. So if you plug in any x value into the psi function, you definitely get a non-negative value. And the one up here is just a flip and a translation with respect to the y-axis. So it makes sense that phi x would be non-negative. So with just these 4, we know a lot. We know that phi is continuous. We know that it's infinitely differentiable. We know that outside of the unit ball, centered at 0, it's equal to 0. We know that at 0, the function takes on the value 1, and we know that the function's non-negative. The only thing that we really need to check now is that phi x is less than or equal to 1 inside that unit ball. And the way we show this is through algebra, but also a picture. If you graph these psi functions that are up here separately, and I put them on the same graph, they look like this. You can do that in Desmos if you want. So this is our picture, and we look at x values between -1 and 1. And we want to show that, well, first off, the function is increasing as we go this way and decreasing as we go this way. It's not hard to show that those functions are strictly positive in between -1 and 1. And then we're going to multiply the two together and figure out that the peak occurs at 0, which means that for any input in between those, we're between 0 and 1. And it's just algebra. So I multiply these together, apply definition, multiply them together. And then we want to add the fractions, so we do that. Simplify a little bit. And we notice that the denominator should be always positive, which makes sense. And as x gets big, the denominator gets small. So if I want to maximize this guy, we got to get close to 0. And the numerator is negative too. So by a very heuristic argument, if I'm using that word correctly, I'm just claiming that the product of these two is maxed out at x equals 0. Perhaps I could write some more details, but for the purpose of this video and the sake of my scrap paper, I'm just going to leave it at that. Plus, when I presented this at the board, that's basically what I wrote, and they said, it's fine. You can keep moving. All right, and then the last thing to show is that the derivative is positive on this interval, and the derivative is negative on that interval. And you can pretty much just use calculus to show that. And then using that, we see that phi has the global max at 0. And then we're basically done. We have our bump function. Why is the bump function so important? Oh, it's useful when we want to convolve something, whenever we're using convolutions. Because convolutions are very useful in applied mathematics, I've come to learn. I should probably take more applied mathematics courses because that stuff is generally pretty interesting. I don't have like a preference. Well, okay, I do have a preference for pure math because I do like the spirit of mathematics more. Some people are like, I like math, but I need to have context with it. I need to know why we're doing all this stuff. I need to, they want to solve real world problems, and that's their outlook. For me, I just wanted to understand the philosophy behind a lot of this stuff. And so that's why I gravitated more to pure math than applied. But that's not to say I'm not interested in applied, because when I took calculus, I loved calculus because we were solving some very novel problems, at least novel to me. Like, there were some things that I never dreamed of being able to figure out on my own in middle school without calculus. So for that reason, calc was my favorite subject in school. Of all the classes I've ever taken, calculus was my favorite, by far and away. So stuff like this speaks a lot to me. Anyway, this problem was probably a bit long-winded. I mean, we're at 32 minutes, 33 minutes now. But I hope you got something out of it. I did, because I learned a lot by going through this, actually. There's a lot of neat tricks in here that become useful when you're doing problems in analysis. So as long as, and I'll say this, I don't think it's terrible, because I did get this out of a textbook. I don't think it's terrible to copy a solution out of a book or on the internet, but just make sure that you make it your own and you understand the steps along the way, and that you incorporate the methods and tricks. I say tricks, but they're really just like tools used to help solve hard analysis problems. As long as you incorporate it into your repertoire, I think it's perfectly acceptable. Let me know what you think. I hope you enjoyed this video. Thank you for watching my videos in general.